There is an aspect of this that is like drinking from a fire hose, so if you don't pick up on everything today, do not be surprised. I'm going to skip a bunch of stuff today. I'm going to skip the entire manned spaceflight program. So we're not going to talk about the shuttle amateur radio experiment. We're not going to talk about Mir, the old Russian space station that lying at the bottom of the ocean somewhere, but had hams on it for a long time. I'm not going to talk about the International Space Station, but I will do that another time. Right now, there's nothing on the space station that you can work through or talk to. Occasionally, the astronauts will show up doing a school contact, and you can usually hear that if you're in the footprint. But there is no current general operations from the space station, so we'll talk about that another time. When the new equipment gets up there, that would be a better time to talk about it. We're not going to talk about Johannes Kepler and all his work in the 17th century. He's a very smart guy. He's a very smart guy, or was a very smart guy. He's actually dead now. He figured out all the laws of planetary motion, figured out orbits and stuff, which is impressive because he didn't have any actual spacecraft. So he couldn't do any measurements. He had it all done with, he didn't even have a slide rule, pencil and paper, and his telescope. He improved on Galileo's refracting telescope. NASA has a really good video on orbital mechanics that if you're interested in this stuff, I highly recommend you look at. I will get that. We'll whip up a satellite page and I'll put the link on there. It's about.
There's already a page, but we'll put it on.
Okay. It's about a 25-year-old video, but orbital mechanics hasn't changed since at least the 17th century, so it all still works. That's where we get the name Keplerian elements. The Keplerian elements are distributed. They describe the orbit of the different satellites based on the work that he did 300 years ago. It used to be kind of a deal to get this information and put it into your computer and have it spit out all your predictions. Now, a lot of people use apps on their phone and you just say update and it goes and pulls the new information and it displays it on your phone. It's a different world than when I started playing with satellites 25 years ago. I'm going to skip all the satellites that haven't been put up by AMSAT North America, and there are lots and lots of them. There is actually a number associated with the amateur radio satellites, and we're up to 92. And that, not all the amateur satellites have those numbers. We're going to skip all the Russian radio Sputniks. We're going to skip all the Chinese satellites, and there are a lot of Chinese ham satellites. We're going to skip the AMSAT UK FunCube series. There's a bunch of satellites, I think they're up to 3 of them now, 3, 4, 5 of them now, specifically designed for kids in school to copy the telemetry and learn about space environment and that type of thing. I'm not going to talk about those. I'm not going to cover all of AMSAT North America's satellites. So, moving on. Everybody knows. Will and Sun. All right, never mind. Earth satellite is anything that is in orbit around our planet. The moon is in orbit around our planet. That's classified as a natural satellite. There are asteroids and other objects in that category as well. Everything else that's in orbit is man-made, as far as you know. Man-made objects are referred to as artificial satellites. I decided I better put in a whole section on buzzword compliance. First one is Oscar. Oscar is my dog. He came with that name. I promise you I did not name him Oscar on purpose. Oscar stands for Orbiting Satellite Carrying Amateur Radio. Clever, isn't it? Came up with that a long, long time ago. We're going to go over, this is going to be a little heavy on the history and a little light on the technology. I think the history is really important because a lot of people don't understand that we have had amateur satellites in orbit since 1961. That's a long time. There's some of you that were born, well, I was born after 1961. Not much after 61, but we've been in space a long, long time. We'll talk about modes. The modes are the names that we assign to combinations of uplink and downlink frequency bands. We'll talk about that more later. We'll talk about what AMSAT calls phases. This is just a description of the evolution of the satellite program that we've been doing now for well over 50 years, almost 60 years, and not too long. I'll explain that more later. Danny? Oh, I'm sorry. AOS is a term you will see a lot when you start learning about this stuff. It means acquisition of signal. Satellite has come over the horizon in your location, and now you can hear the signal. TCA, time of closest approach. Every satellite traces an arc across the sky from your location, and that we'll talk about where that arc is and how to find it. The time of closest approach is the highest point in that arc. That also corresponds to the point where the satellite is nearest to you. LOS, opposite of AOS, is loss of signal. Spacecraft is setting, dropping below the horizon. Once it's below the horizon, you can't hear it anymore. Apogee is the term used for the furthest distance in a satellite's orbit from the Earth. Perigee is the other one, the closest distance. Most of the satellites, the amateur satellites currently in operation, have nearly circular orbits. So their apogee and their perigee are either the same or very close to the same. That hasn't always been the case. We'll talk later about the phase 3 satellites, which were high Earth orbit satellites. Their apogee was on the order of 40,000 kilometers in space. Talk about the orbits. Low Earth orbit, where most of our satellites are. Anything below 2,000 kilometers altitude above the Earth. Is that your phone, John?
I don't know.
Sounds like the EDS tone. Geo is the other one, geosynchronous Earth orbit. As the orbits get higher and further away from the Earth, it takes longer and longer to complete an orbit. A low Earth orbit satellite, when they're 500 or 600 kilometers above the surface, takes about 90 minutes to complete one orbit. As you get further out, it takes longer and longer, and in fact, when you get out to 35,786 kilometers, that's the point where the orbit takes exactly 1 day. So we call these geosynchronous Earth orbits because they hang in one spot in the sky. There's actually a special case of geosynchronous called geostationary, where the angle of the orbit is at 0, which is where all the Dish Network and XM satellites and all those things sit. They sit, and their rotation matches the rotation of the Earth, so from your point of view, they never move. We don't have any satellites there for amateur use yet. But believe it or not, we're working on it. Medium Earth orbit is anything between those two endpoints. 2,000 kilometers and down is where the low Earth orbit stuff is. Above 35,786 is where the geostationary stuff is. There's also high Earth orbit stuff, and we used to have satellites there. That's where the apogee is greater than that number. And those satellites, when we had it, was in a highly elliptical orbit. So it would actually come close to Earth, and then it would go back out and hang there, and then come back and go out and hang there. Stole this from, how did that turn out? That didn't turn out very well, did it? I tell you, that looked way better on my laptop screen. Earth, right? There's a very faint line that you probably can't see because I can barely see it, which is the geosynchronous satellites out here. AO 40, Oscar 40, Oscar 13, our old phase 3 satellites were in a highly elliptical orbit. So they'd go out here and they'd hang out here for 8 hours at a time, and then they'd swoop back in and come back up. We don't have any of those in orbit currently. Yeah, that didn't come out at all. That doesn't bode well. The only part of the Kepler stuff I'll talk about is the orbital inclination. That's the angle made between the plane of the orbit and the plane of our equator of the Earth. You can launch a satellite into just about any orbital inclination. Prograde orbits, the inclination is less than 90, that's most of our stuff. When we do that, the path runs from west to east. It'll rise, the satellite will rise in the west, either southwest or northwest, and it'll end up in the east. A retrograde orbit, where the angle of inclination is over 90 degrees, it's the opposite. It appears to be going east to west to us. And we're going to show some live satellite tracking here in a bit, and you'll be able to see that. That also determines the north and south limits of the ground track as well. And both of those things together determine the footprint. Now, what is the footprint? That's a combination of the height of the satellite and its orbit, and determines who you can talk to. This was way too late last night. I snapped a picture of Oscar 85. I'm at the house there. Can't really see me in the house there, but I'm in the house there. Just as that was coming over, as I was able to acquire the signal, I can work anybody. Is there a laser on this?
Yeah.
How does it work?
Center button.
Oh, like that. Oh. I can work anybody in that circle. Now, granted, there are not many people up here, but there's a whole lot of people right in here. And I can talk to anybody. And as the satellite moves through its orbit, which is this blue track here, that's going to move. Now, I'm going to move out of it at some point, but as long as I'm in this circle, I can talk to anybody else that's in that circle. Here's another example. That's Saudi Sat Oscar 50. Footprint's a little bit different because the altitude of the satellite's a little bit different. You can see I could work. You can't see that. If I was to talk through this satellite, I could talk to anybody in this circle, which means the entire East Coast, most of Canada, most of the Midwest and the mountain states, and also most of the Caribbean. So even with a low Earth orbit satellite, there's a lot of VX to be had. We can talk about Doppler Shift. And I had a video, but you know what? When you use PowerPoint on a Mac, and then you take PowerPoint and use it on a PC, the video gets goofed up. Surprise, surprise. So, to demonstrate Doppler Effect, if we can make that full screen, and we can get the audio to work.
Yep.
Now, it turns out that Doppler, who was another scientist way back he was in the 1800s, I think, figured out what was going on here, and as that wave moves towards you, it's moving towards you, it's higher than it actually is, according to your ears, because the wave is being compressed. As it passes you, did you notice that the tone of the horn all of a sudden dipped down, right? It turns out it doesn't matter what frequency is in use. It could be an audio frequency like a train horn. That train horn is actually constant. If you stood next to the horn and pulled the cord, it's a solid tone. But because that's moving with respect to us, the observer, it appears to drop down like that. Well, it works the exact same way with radio frequencies on satellites, except they're going a lot faster and the frequency's a lot higher. And that's what Doppler figured out a long, long time ago. So when a satellite is far away from us and we're listening to it, we have to tune high because that frequency appears higher than when it was actually transmitted. As it passes that TCA, the time of closest approach, that frequency drops down. And as the satellite's moving away from us, it's actually at a lower frequency, so we have to tune down. It's exactly the reverse for the transmitter. You've got to tune low when they're coming towards you, and then you have to tune high when they're leaving. Because from their perspective, it's reversed. Frequency doesn't matter if it's audio or RF, works the same. It is proportional to frequency, so the amount of the shift changes with a higher frequency. So where there may be just a couple of kilohertz difference at VHF on 2 meters, it's going to be 3 times that much on 70 centimeters because you're 3 times higher in frequency. When you get up to L band and S band and all the microwave stuff, that Doppler shift gets really big. There's software that will tune your radio for you. For the low Earth orbit stuff, it doesn't matter quite as much. You can set up your channels in your radio with the appropriate steps in it, and it'll work adequately. So, moving on. First Earth satellite, first artificial Earth satellite.
Sputnik.
Exactly. I don't know how to pronounce that.
Sputnik.
Yeah, I know. 1957, October. It was just a sphere, 58 centimeters in diameter, weighed about 83 kilograms. Had HF transmitters just above 20 megahertz. Anybody know what's at 20 megahertz? WWV. So anybody that could receive WWV on 20 megahertz could listen to Sputnik. There was another signal on 40.002, depending on which source you looked at. People pretty quickly realized that the timing of the pulses indicated the temperature and the pressure in the satellite itself. Completed 1,400 orbits in 22 days, and then the batteries died. Looked like that. It's a simple sphere with a bunch of dipole or monopoles hanging off it. Can you click that? Can I click that?
Switch.
There are hundreds and hundreds and hundreds of stories of hams listening to this, and all their neighbors gather. Does anybody remember this?
Yeah.
Okay. Did you guys actually, were you able to listen to it live? Did you know anybody?
You weren't a ham.
You weren't a ham at the time. A lot of people did this. One of the stories that I read, the campus ham station picked it up and they tuned it and they recorded it, presumably on a reel-to-reel tape recorder. And then they played it over the campus radio station, and then government men in black sedans showed up and confiscated their tapes. And there's all kinds of stories like that. Because it was a big deal.
Yes, it was, but
It scared the bejesus out of everybody.
it did.
And it led directly to the space race that we all remember from the 60s. And it actually led to a lot of good things, because everybody thought, wait, what? Moving on. What was the first artificial Earth satellite launched by a non-governmental organization? Oscar 1. Our satellite was the first one that wasn't launched by, it wasn't built by NASA or built by the military or built by anybody else. It was Project Oscar, which is a bunch of hams in Silicon Valley, most of whom worked for defense contractors and were involved one way or another with the space program, but they managed to finagle their way into launching a spacecraft. December of 1961. It was launched as ballast on Discovery 36, which is a Corona mission. I don't know if you remember the Corona. That was the one where the film canisters would come back to Earth on a parachute, and they would catch them. Except that didn't actually work that well, and the film canister associated with this launch was actually picked up by scuba divers, named scuba divers. It was ejected out of the launch vehicle with a $1.10 spring from Sears and Roebuck. You can tell it was a long time ago because people still call it Sears and Roebuck. It was not quite a box. It was about a foot on a side and half a foot tall with a mass of 10 kilograms. It looked like that. The shape is determined by where it fit into the launch vehicle. They had so much space they could fill. There's a backstory to this too. Previous launches of those Corona missions, which are all spy satellites, that's what the film coming back down was, had used sand for ballast. Well, if you're at all familiar with the military procurement system, this was very special sand. It was very expensive sand. It could only come from a certain beach in a certain state in a certain congressional district. And somebody got wind of that and said, could you do something useful instead of paying $10,000 a pound for sand? And they said, well, we'll see what we can do. Oscar 1 ended up replacing that sand. Lance Skinner, K6GSJ, is still alive and goes to some of the MSAT stuff. I assume he was probably the youngest guy in Project Oscar, or he drew the shortest stick because he was the guy that had to build it in his basement. And that's him in his Radio Shack. And I gotta say, this is at home in his basement. He's got a pretty impressive station there. So he's either living with his parents or doing very well. I don't know which, but he's got a well-equipped station, really does. And he's building the first non-governmental satellite. I mean, that's impressive.
He's single.
Single, yeah.
Yeah, wedding ring on.
Yeah,
Either way.
either way.
So you got a ring on there. He's married.
Well, yeah.
He must have an understanding wife.
I think I'm building a satellite for outer space.
Or she's got a license too.
So it only had a beacon. These were referred to later on as bleepsats because that's all they did. It was a 140 milliwatt transmitter into a 2-meter antenna, 144.983 megahertz. A monopole antenna. All it did was repeat HI, 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 HI. That speed actually varied with temperature, which was not a design of Oscar 1. They figured it out after it launched. Later Oscars, they actually took advantage of the fact that that was a known quantity and figured out what it meant so they could actually get some rudimentary telemetry. Lasted 312 orbits over 3 weeks. Batteries finally died. There were no solar panels or anything on this. Go ahead
So
and click that.
it was essentially laughing at us, right?
HI is the telegraphic laugh.
Right.
And if Mark can click on that thingy there. Hey.
Hey.
Hey. You hear it? Sounds like crickets. It's HI. Oscar 2, same idea, beacon only. 6 months later, June of '62. We actually built another one just like it, but we decided to put all our energy into Oscar 3. That took another couple of years. Also had a transmitter on 144 megahertz, but had a receiver on 146 megahertz. A full watt, the transmitter was, and it had a 50 kilohertz wide linear transponder, which is actually pretty impressive for 1965. We still use linear transponders on a lot of satellites today. They receive whatever they hear on a certain frequency and transmit it back on another frequency. You can have multiple signals within that 50 kilohertz passband. They don't use FM, they generally use SSB or CW, and they're basically, it's a bent pipe, and whatever goes up comes back down again. This one actually had a photovoltaic cell on, a solar cell on it, so it actually was able to last a little bit longer. As far as is known, 98 stations were able to make QSOs in 1965 via satellite, which I gotta say must have been pretty impressive back then. Again, beacon for temperature and battery voltage. Oscar 4, 6 months later, launched. Unfortunately, went into the wrong orbit. It had a 70 centimeter receiver and a 2-meter transmitter on it. Because it went into the wrong orbit, it didn't last long. There's only 7 known QSOs. This was the last satellite that Project Oscar launched because in '69, the Radio Amateur Satellite Corporation was formed, which we know as AMSAT, and they took over the shepherding of amateur radio satellites. Launched a bunch in the early '70s, 6, 7, and 8, much more capable than the early stuff. Thousands and thousands and thousands of QSOs. They call them Phase 2 satellites now, but they didn't actually call them Phase 2 satellites when they were built. They didn't call them that until the Phase 3 stuff came out. When they started with the Phase 3, which we're going to talk about here in a bit, in '75, they decided that this was the third phase of the satellite program because the first phase was all those little bleepsats back in the early '60s, and then 6, 7, and 8, those were Phase 2, and these new ones are going to be Phase 3. But now everybody thinks the other ones were called. Retcon means retroactive continuity. You'll see that in the science fiction stuff where some story now doesn't make sense based on previous episodes and they have to fix it all. If you're into Star Trek, you can get into long arguments about continuity with the new Star Trek. Oscar 7. It's actually in a fairly high orbit, 1,400 kilometers. It's almost out of the low Earth orbit space. It's at 101 degree inclination, meaning it's retrograde, meaning it appears to go from east to west instead of west to east. It was so capable, we had to introduce the concept of modes. We had a 2-meter uplink with a 10-meter downlink, called that mode A. We had another one that was 70 centimeters up and 2 meters down, called that mode B. Mode C was the low power version of mode B. Mode D was a big blah, 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 blah. We're going to talk more about modes in a minute. It had radioteletype telemetry, so you could actually get a lot of information from the satellite. It had sensors built in, and the internal housekeeping unit computer would actually gather up that information and send it out as teletype. Had a code store experiment. You could load messages from the command stations, and these would be sent out as a beacon in Morse code. It actually had an S-band beacon as well, 2.4 gigahertz, which is where a lot of Wi-Fi is today. That's what it looked like. It was quite a bit bigger than the previous satellites. Oh, and it died. And then it came back to life. It was launched in '74. One of the batteries shorted out in 1981 after 7 years, which is a pretty good run. 7 years is not bad for a bunch of people that they know what they're doing, but they're not professionals. And then in 2002, that short opened up. So that when the spacecraft was in sunlight and the solar cells were active and were providing voltage, the satellite actually came back to life. And you can still work it today. 16 years after it came back to life, which was 7 years, or no, more than that, nearly 20 years when it had been dormant, and 7 years before that. Still up there, still in orbit, people work it all the time. When it gets eclipsed, when it goes into the part of its orbit where the solar cells are not illuminated, it turns off. Sometimes it comes back up in mode A, sometimes it comes back in mode B. It depends. They don't have control of it. The control receivers are non-functional, but you can still use the linear transponder on it. Middle of the 70s, when this stuff was going on, we got serious and came up with phase 3. US, Germany, UK, Japanese, others decided to put stuff in high Earth orbit. They built a number of tri-star space frames. I'll get a picture of those here in a bit. They used a Molniya orbit, which is what the Russians use for a lot of their communications satellites, because it's that highly elliptical orbit that comes in close to the Earth in the southern hemisphere and then it goes way out in the northern hemisphere. So it hangs very high over the northern hemisphere. Remember, a lot of Soviet Union is way high north. So the geostationary stuff that's over the equator doesn't work so well when you go way far north in the Soviet Union. So they came up with this Molniya orbit, and that's what they chose to use for the highly elliptical stuff. Hangs over the northern hemisphere for hours and hours. Had a bunch of different transponders on it, lots of power, relatively speaking, and they had motors on. They had rocket engines on. That is good and bad. That's the basic design. As far as I know, they built 5 of these, just like this. That's a schematic drawing of one, or an artist rendering of one. You can see the different antennas, directional antennas here. They have HF antennas, all kinds of stuff, dishes for the microwave stuff. And if you look back there, you can see the cone of the rocket motor. So we actually had the ability to change orbit. That gives you an idea of the scale. Those are regular-sized human beings there with a full-size mock-up, or that may actually be a flight model, I'm not sure. But that's about the size of them. Phase 3A was the first one. Launch failed. It was going up on an Ariane rocket from French Guiana down in South America. Launcher failed, took the satellite with it to the bottom of the ocean. Space is hard. I'm going to keep coming back to this. Space is hard. Phase 3B, another one of the tri-stars, very similar capabilities, successfully launched in '83, collided with the launch vehicle. So it didn't quite end up in the orbit that everybody wanted it to end up in. A couple years later, radiation killed the internal housekeeping unit. Space is hard. However, most of the transponders ended up working, and thousands of people, including me, made QSOs via Oscar 10. It worked after people figured out what the orbit really was and figured out what transponders were on, and when they were on, it actually worked somewhat. So another TriStar available. Put it up in '88, Oscar 13. This was probably No, not probably. This was the most successful of the phase 3 satellites. 720 kilometer perigee, but look at the apogee, 38,000 kilometers. That's way out there. That's past all the geostationary stuff. 56-degree inclination of the orbit, a Molniya orbit. It would hang above 30,000 kilometers for 8 hours at a time. It was great for people in the northern hemisphere. Not so much for the southern hemisphere, but most of the money came from the northern hemisphere, so we favored the northern hemisphere. This thing weighed 140 kilograms at launch. By the time the fuel was all expended, that's a lot of fuel. We're down to 90 kilograms when it was empty. There was a packet experiment known as RUDAC that never actually worked. There was an L-band receiver that was about 10 dB less sensitive than it had been designed to be. The 70 centimeter receiver failed in 1993, which cut out a lot of potential QSOs. And it finally deorbited itself in 1996 because the fuel had been exhausted. So space is hard. Sometimes it all kind of works out. Then they got crazy. Phase 3D, after a huge fundraiser, I don't know how many millions it cost to build Phase 3D. They finally put it up in 2000, became outside Oscar 40. It was 600 kilos when it was launched. Double that and add 10%, that's what, 1,500, 1,600 pounds? It's a half a ton. This is like a real satellite. It was so capable and had so many transponders that they had to redo those mode designators because it didn't make sense if you were going to give one letter to a pair of frequencies, you run out of letters. Let me take a little detour here and talk about those modes. A07 had mode A, where you could go up on 2 meters, come back down on 10. Mode B, 70 centimeters up, 2 down. Mode C, low power, et cetera, et cetera. We talked about those. For phase 3, well, it turns out the Japanese like to use 2 meters up and 70 centimeters down. So I don't know, mode J, because the Japanese. And there's a digital version of that too, so JD. And we're doing the microwave stuff, so let's use those the letter names that they have for those bands. So we'll have mode L, and we'll have mode S, and we'll have that kind of stuff. This is a chart out of March 1995 Funkometer, which is a German hand magazine, that shows all the different uplinks and downlinks for phase 3D. And you see we run out of letters pretty quickly. So what they decided to do was use letters for each band and then pair them together to indicate the uplink and downlink. This didn't come out well either. Here's the phase. This is Oscar 13 columns here, and this is phase 3D, which became Oscar 40. The EIRP, which is the transmitter output plus the gain of the antenna, 180 watts on 2 meters, 300 watts on 70 centimeters, 8 watts on S-band. For phase 3D, that's 2,500 watts EIRP, not 2,500 watt transmitter, but with the gain of the antenna. 8,000 on 70 centimeters, 4,000 on S-band, 5,000. This was a huge satellite, very powerful. I mentioned it had a rocket engine, right? So we decided to give letters to each band, and this is the same system we're using today. We give a pair if it's up on 2 meters. Here's the old format just sort of happened, and they didn't think it through. New modes, we name the uplink and downlink specifically. So the old mode A became VT. V is the uplink, 2 meters, 10 meters down. T is the downlink. Mode B is now UV, and we actually have a lot of UV satellites up there now. Mode J became VU. We also use the other letter bands for the microwave stuff. There's no consensus on the styling of this. The initial stuff was the first letter. It's always the first letter is always the uplink, and the second letter is the downlink. This was the original style, but a lot of people render it this way, and a lot of people delete the slash. It means the same thing. Don't worry about how people write it down. That's what it means. There's a UHF uplink and a VHF down. So the end of the detour there. So it was so capable, they had to change the modes around. That's the satellite right there, rocket motor. That's actually in a carrier. That's not, this is the satellite here. This is part of the carrier that launched it. There it is, again, to scale with some full-size humans. I don't think you can read this, but it says remove before flight. There
Is that
it
the
is.
pitot tube?
Huh?
Is that the pitot tube?
No, this is the rocket motor here, and there's a plate in there that prevents crap from getting in it before.
No, I was just joking on a
Oh,
airplane
okay.
says remove.
Okay, all right. So, the story is, and nobody, I have not read this in an official thing, I have seen stories that this was not just a little plastic cap like on your Folgers can after you've peeled off the metal top and then you put it back in the fridge with the plastic thing. It wasn't one of those. It was because a lot of German guys worked on this, and I don't know if you've dealt with German engineers. This was an engineered piece of metal that fit in there, and there were set screws, and it was all very precision oriented, and it didn't get removed. That became a problem. Space is hard, did I mention that? When they were testing the motor, when they were trying to change the orbit, they presume an explosion occurred when the rocket was ignited and that cap was in place. They don't really know because there's no way, they can't go and visit it. You can't see it. But they presume that's what happened. Unfortunately, it took out most of the transponders in the lower bands. So the use at that point was limited to the microwave stuff. Did I mention space is hard? Last contact with the satellite was February 2003. So this actually, not only did it blow a hole in the satellite, it kind of blew a hole in AMSAT too, because this was a lot of money. It cost a lot of money to build it, cost a lot of money to get it to orbit, and there wasn't a lot of money left, and there was a lot of people that were really, really bitter after this happened. Because, and that's why I keep harping on this, space is really hard. If you're gonna play in this, you've got to expect that not every satellite is gonna make it to orbit, and even some of the ones that do, the rocket motor's gonna explode. So AMSAT was kind of left in the early '80s in a kind of a precarious position. Did I mention space as well? Nonetheless, it carried some experiments on it, including this RUDAC experiment, which was a packet thing for sending data back and forth. There was a GPS experiment that allowed the satellite to receive the GPS constellation from above the GPS constellation, because that GPS constellation is in mid-Earth orbit, so it's a 3,000 kilometer orbit. This was way above it and was monitoring signals from back. This study actually gets cited quite a bit in space physics journals and stuff. So, despite all the problems, we managed to get some science out of it, which is pretty good. I mentioned space is hard. Space is also expensive. We used to be able to con our way into launches. I mean, you look at Oscar 1, right? We replaced sand. Pretty good. Didn't pay a lot to get into space. That's all gone. By the mid-2000s, that was gone. Space was, there's so much stuff up there, it's getting hard to keep track of it all. And I mean that for real. Space debris is becoming an issue. Because there's so much stuff up there, there's so many launchers out there from so many different countries, and it all costs money. So they decided to focus on smaller spacecraft. They came up with ECHO as a follow-on to Phase 3D. Next letter is E, although that doesn't really work in how they have the phases, but never mind that. This was launched in 2004, became AMSAT Oscar 51. It's in a nearly circular orbit, retrograde, about 11 kilometers, about a foot on a side. I didn't go through the 1990 launch where we sent 5 microsats up from different countries. They were about a foot on each side, weighed about 11 kilos. This was the same format space frame, but the innards were 24 years newer. So it was a pretty capable satellite. It had a 10-meter PSK uplink. Had uplinks on 2 meters and on L-band, and downlinks on UHF and on 2.4 gigahertz. Multiple channels for each one. It had FM, it had analog, it had digital, it had a whole bunch of stuff. So even though it was in low Earth orbit, it had a lot of stuff on it. It had a lot of transponders on it. Last heard from around Thanksgiving in 2011. They had already started working on the Foxtrot program, Fox actually. These are even smaller. These are 1U. The folks that put up these microsats a long time ago standardized on a size called a U, where they're 10 centimeters on the side. That's a full-scale model of a Fox satellite. And we have 3 of these in orbit and 2 more ready to go. And I'll pass this around. Solar panels on each side of it, transponders inside of it. I'll show you not an exploded view, that's probably a bad word to use, but a cutaway view. Space is hard. But I'll pass that around, pass that back. But that's a full-size mock-up. Only weighs about 1 1/3 kilograms. It's a standard design. We built 5 of them. We left room in there for experiments so we can partner with universities to not only subsidize the project, but also to open up various avenues to space. It's in some cases easier for a university experiment to get space on a rocket than it is for a bunch of ham radio operators. These things all have telemetry. It uses a technique called data under voice. If you know how a CTCSS, a PL tone works, it's so low you can't hear it. You actually can hear it if you have a good set of speakers, but very low. Well, if you think of this as a modulated CTCSS tone, you can actually get about 200 bits per second of data in there, and that runs all the time when the satellite is transmitting, which is all the time pretty much. There is a Fox Telem program that allows you to decode that and forward it to a server that collects it up and sends it back to the people that are doing the experiments. AO92 also has a high-speed 9600 bit per second telemetry system. The antennas are nitinol, just like the antennas a bunch of us bought. It's that one handy. You can tie them in a bow, you can tie them in a knot. So they wrap them around, if you look at the model when you get it, they're wrapped around those little posts that stick out there. There is it's tied down with a fishing line, and the fishing line is wrapped around a resistor. And after a timer expires, so that the satellite knows it's out of the launcher for a long enough time, a voltage is applied to that resistor. And what happens when you put a voltage to a resistor? It gets hot. It cuts the fishing line, and if you've played with these nitinol antennas, you know that once they're straight, they want to be straight forever. So once that fishing line lets go, it goes boing, and the satellite antennas come up. That's an image of it. You can actually see the antenna is stowed here. All wrapped around those pins. There's a connection for the other end of the antenna that's live, so that they know if the resistor has burned and the fishing line is gone and the thing deploys, it loses that connectivity, and so it knows that the antenna has been deployed. Otherwise it won't transmit. That's the cutaway, we'll call it the cutaway view, not the exploded view. All the Foxes look like this, multiple boards. You can see the connectors here between the boards. There are power buses through these. There are a bunch of roughly D-cell sized batteries inside, and again, there are solar panels on every face of this to keep it powered. We have transmitter, receiver. IHU is the internal housekeeping unit. That's the small computer that keeps track of everything and makes sure everything is working. It does all the housekeeping of the satellite. Power is managed in here. There is a maximum power point tracking module built by some guys at, and I don't have a slide of that. Some university, I think it was in Rochester, anyway, RIT maybe. Anyway, built the MPPT tracker in there that keeps the batteries charged with the solar panels, because the solar panels are moving as the spacecraft tumbles. But then we left a bunch of room for other experiments, and we have actually been pretty successful in partnering with universities and getting other experiments on board of these. That's one of them. That's the University of Iowa's high energy. I'll go back here. Should have put these in a better order. Well, anyway, we'll get to it. It's a radiation experiment, and that's the board. They build that board, it gets assembled into the spacecraft. Fox 1A went up in 2015. became Oscar 85 on orbit. Not quite circular, but pretty close, 518 by 810. It's the perigee by the apogee, 65-degree orbit. Carries a low-energy proton radiation experiment from Vanderbilt. It carries a gyroscope experiment from Penn State Erie. Operates on UV, and it's FM. So you can use a handy-talkie, and I'm dead serious about that. You can use a handy-talkie. You usually need more than your rubber duck antenna, but you can use a handy-talkie. On Fox 1A, the first one we put up, just before the spacecraft was integrated with the launch device that goes into the rocket, the antenna broke. And there was no time to do the special soldering to repair it, because it takes some kind of special solder to put it back on. I don't know the details of that. So they used conductive epoxy glue. I didn't know there was such a thing, but they used it. It was expedient, got the job done. However, the antenna is not nearly as sensitive as they had hoped. Space is hard. But it works. Now, it's almost impossible. Now, you got to be good to get in with a handy-talkie and a small directional antenna on Oscar 85. That's the downside of it. If you're on a mobile rig or you're at home, it's not hard at all. And the transmitter is very strong. You can easily hear that on handy-talkie. Fox 1B, also known as RadFX-SAT, was launched just this past November, just before Thanksgiving. Became Oscar 91 on orbit. Similar orbit to the other satellite. This one, because it's actually Vanderbilt satellite, that's the way people think of it. It's the RadFX-SAT, and it also happens to be ours too, but they have a experiment that's looking at the radiation effects on off-the-shelf components. So they're putting up just regular old parts up there, not specially hardened for radiation, not space qualified, just regular common off-the-shelf chips and resistors and that sort of thing. And they're trying to find out how radiation affects that stuff. Also mode UV FM. Fox 1D went up just 2 months ago. Oscar 92, similar orbit to the other ones, a little lower apogee. This one has that, there it is, high energy radiation CubeSat instrument, Herky. That's the board that I showed you before. Another radiation experiment, because there's considerable radiation, as it turns out, when you get out of the atmosphere. Virginia Tech has a camera on there as well, so it's actually able to snap photos. And we have a gyroscope experiment. This one is mostly in mode UV, but sometimes it's in mode LV because it has an L band, 1200 megahertz uplink. Now there's a schedule for all this stuff because when the high-speed telemetry is on, you can't use the transponder. You can't communicate through it when the transponder's on. So there's a published schedule that tells you when that's going to happen. The L band uplink can be turned on by the command stations. The L band and the U band uplinks are not active at the same time. It's one or the other. Likewise, when they're running the camera uses that high-speed telemetry as well, and the satellite's unavailable. But on the AMSAT website, there's a weekly schedule that tells you when all this stuff's going to happen. Fox 1C, or Fox 1 Cliff, was named in honor of K7RR, who's a silent key and who was a longtime supporter of AMSAT and who left a sizable bequest in his will, so he gets the satellite named after him. Hopefully that's going to go up in the third quarter this year. It's basically the flight spare of Fox 1A, so it's going to be almost identical to it. It's got that low energy proton experiment and a gyroscope experiment, also UV-FM, so we're hoping that goes up here pretty soon. There's another RadFX-SAT, Fox 1E, also hopes to go up third quarter this year. This one is also looking at the common off-the-shelf stuff, commercial off-the-shelf stuff, but different components. This one has a linear transponder. So you go up on 2 meters, you come back down on 70 centimeters, but it's linear. The linear transponders support SSB and CW, so you'll be able to tune in, send lower sideband up, it inverts it to upper sideband and listen on upper sideband, or CW. There was always expected to be a Fox 2 program. Somebody wanted to make sure that this had a greater orbit and a larger footprint, because remember, as the orbit gets bigger, the footprint gets bigger. And so somebody decided, yeah, let's do a greater orbit, larger footprint. Hey, wait a minute, that's golf. These are going to be bigger than 1U, probably 3U to start. We're gonna have different capabilities in these. Some of them will be LEO, some of them will be MEO, some will be EO, depending on, again, on the launch opportunities. Amazingly, 2 missions have already been accepted, just 2 last week.
Woo-hoo!
Yeah, NASA has said, yeah, we'll take that for our CubeSat launch initiative. So this is gonna happen. It's gonna be a while. Golf T is the first one, because, you know, once you start with the acronyms, right? Technology Evaluation Environment. Radio Output Login, Golf T. Similar, it's going to be similar to RadFX Sat2, but it's also going to have a field programmable gate array software defined radio. We hope in the future to use this same 5 and dime style of communications, 5 being 5 gigahertz, dime being 10 gigahertz, or mode CX, for high Earth orbit stuff. If we get to geostationary orbit, which we may, it's going to be 5 and dime. So that hopefully will be on this first Golf mission as well. So we'll be able to check that out actually in space instead of on test benches. 2009, by the end of, NET means no earlier than, and I'm sure that launch date is going to slip. I guarantee it. Golf 1 was also approved. It's going to be a couple years after that. Both are going to LEO. I don't know what the details are of Golf 1. It'll be a follow-on to that other mission. Is there other stuff? Oh, yes. Yes, there is. The Germans would very much like to put the last TriStar space frame in high Earth orbit. If you Google around for Phase 3 Express, you'll see lots of glowing reports of how this is going to happen real soon now, but they're all dated from about 5 years ago, unfortunately. It's hard to get into higher orbits and much more expensive. Is there a Phase 4? Why, yes, there is. Phase 4 is anything we put into a geosynchronous orbit. And there are 2 projects, one of which is going to launch this year. That's the Phase 4A. The guys in, I think it's Qatar? Is it Qatar? One of the Arab countries. One of their princes is a ham, and he said that there was going to be a geostationary satellite, so there's going to be one. And it's actually getting close to being launched. We are not in the footprint. Again, it's geosynchronous, so it just hangs in space over the same point, or the same set of points. America, and a very, very eastern part of South America maybe is in it. But it's mostly over Europe, Middle East, Africa, and part of Asia, as you can imagine, because they're the ones launching it. There is a Phase 4B, which we hope to get up, that will be over the Americas. This is dependent on a lot of things falling into place, and again, if you Google for Phase 4B, you'll see lots of glowing reports about how this is imminent. Well, okay, maybe. In the meantime, we're working on that 5 and dime system, which will give us 5 gigahertz up and 10 gigahertz down. The current plan is for this to be a digital satellite. It's going to use the same format as the direct broadcast TV satellites, except it's not going to broadcast TV, it's going to broadcast data, which will be broken up into individual streams for audio, video, data, whatever you want it to be. It's going to be a pretty interesting program. There's a Phase 5. Phase 5 is anything out past geostationary, like to other planets, like to the moon and stuff. And the Germans, again, it's the Germans here, it's the Germans here, I don't know what's going on. They're involved in this one too. They're crazy. I hope they don't leave the cap on the rocket. They want to go to Mars. They want to send a satellite to Mars that would be in, Martian orbit, that you would be able to work from Earth. Yes, Mark?
There are hams on Mars?
There are hams we would like to send to Mars.
Yeah.
Let's-
Oh, I got a list.
One right over there.
Hey, you up there?
So the idea would be that you would be able to work, you'd be able to work through this satellite from Earth. I don't know how that's going to work. You're going to need, I think, a long antenna, a really long mag, maybe 600 or 700 elements. I'm not sure. Anyway, they want to do that. Okay, so how can I work these silly things? Well, you have to know where they are in space, and I'm going to have Mark do a little demo here in a second. He didn't know it, but he is. And you have to know where they are in the RF spectrum. That one turns out to be actually pretty easy because they're all listed on the AMSAT website, which Mark's also going to need to have a suitable transmitter, suitable receiver, and suitable antenna or antennas. We're not gonna talk about automated stuff. There are guys that do azimuth elevation and it's all computer controlled, and it really is cool. Been doing that for a long time. When I was in college, we had a setup like that. It was great. We're not gonna talk about linear transponders. We're gonna talk about just the FM stuff today. Mark, if you would bring up a web browser and go to amsat.org.ar. .ar. No, .ar. It's the .ar is the Argentinian, the LU guys. Hey.
Amsat.org?
Take out the www.
Okay. Oh, it's probably not secure either.
No, probably not.
SCAR's webpage is w5nor.org/space. But, there's something else here. Say again, over?
That's it right there, amsat.org.ar.
It's defaulting.
Forbidden.
Looks like the server's goof.
Just drop the S off that HTTP.
Yeah, that'll work. Maybe.
There it is!
Woo! Click on tracking satellites.
This one?
Yep. This is the easiest way to start off tracking satellites if you're interested. There are a lot of them out there, we're going to get rid of most of them. Firstly, click on where it says locator and type in, up at the top there, sorry. It says locator, click that, type in, oh hey, that's actually pretty close, that's close enough. Hit resolve and set new. This is a very smart website. Go up to where it says plus or minus sats up at the top there. And then go down to the lower right and type clear all. And then let's pick a few. Pick the space station, it's right over here. Go down a bit. Aris.
He's
see
not
where it says
looking at the
Aris?
same place you
Oh,
are.
he's not. If I point it is.
Yeah.
Yeah.
Well, hopefully that can be scanned. Where am I
Right.
looking for?
Right there, Aris, that's the space station right there.
First column, about a third down.
Thank you. That's exactly right. Yep, right there, where it says Zarya. Yeah, click on that.
Oh, there.
And then go down a bit more to SO50 Saudi Sat. We didn't talk about that one either, but that's an FM Sat. No, up. Yep, right there. And then go over 2 columns to the top, AO85, Fox 1A, and then go over the last column towards the bottom. You should see AO91 and AO92. Go up a bit for 92, and then go up a bit again for 91.
You at the moon?
But, it doesn't matter, now you can turn that off. Click save this. Now it's much clearer. Now we only have the amateur radio stuff. If you click on any of those, if you hover over them, it'll actually show you a picture of the spacecraft. That's really fun for about the first 10 minutes. If you click on this little bird thing here, it'll stop doing that. And if you don't click on that little speaker, it's going to make a noise every time somebody comes over the horizon, so mute that too. It's already in local time, 11:09, so it's in about 10 minutes. AO90, can you scroll? We're cutting off the far left edge of the screen. Computers, who needs them?
Really? How far left?
Well, that's actually good enough, because that shows you the hours and minutes until that satellite appears at your location, or at least in theory. That's that first column there. Second column is the satellite name, orbit number, we don't care. This is the date that it's coming over. This is the local time of the entire pass. So we're going to have a 10-minute pass here in about 10 minutes. The maximum elevation is kind of low. It's only going to be 5 degrees above the horizon. It's going to come up at 91 degrees. 90 degrees is what? Due east, right? So it's going to be just ever so slightly south of due east. The peak elevation is going to be at 51 degrees, so 45 is northeast, so it'll be a little bit south of northeast. And then by the time it sets, it's only going to be at 15 degrees.
So what you're telling us is it's a satellite that's over Brazil now.
91, yes, that's correct, yes. Yes. So if you click on AO91's blob there,
It just moved.
yeah, it did, it will light up the path, and it will also put a circle that indicates the satellite's footprint. And you'll see the yellow is when it's going to be in our range, and it handily puts the times that it comes above the horizon and the times that set. If I'm quick, I'll be able to get that satellite antenna adjusted and set up, and we can go out and take a listen. I don't know if it'll work it or not. The problem with East Coast passes is that they're East Coast passes. There are a lot of people that live on the East Coast. All of them want to use the satellite. Makes it a little bit difficult from out here sometimes. But we can take a listen, certainly. But this is the easiest way to get started with satellite tracking because you don't have to install anything, it's just a website. If you scroll to the right a little bit, please. This gives you kind of a schematic representation of where the satellite is in terms of your azimuth. Right now it's southeast of us. But because we'll pretend this is the surface of the planet, it's actually below the surface of the planet from our perspective because it hasn't risen yet. When that circle hits that yellow bit there, this line will be here, and it gives you sort of a relative representation of how high the satellite is. Gives you, there, in fact, there it is in numbers right there. If you scroll down a bit, it actually lists out the frequencies. Here it tells that acquisition of signal is going to be 9 minutes 28 seconds. It's an FM voice repeater. Your uplink needs to be 435.242. Now, handy talkies can't tune that close. It's okay. There is automatic frequency control on the receiver, and it's usually good enough to pick up that much slack. You do need a 67 hertz tone on this. It is tone protected. There are a number of places where amateur bands are used by non-amateurs, let's just say. They may or may not have the sanction of whatever their country's telecommunications authority is, usually not. So it was decided that we better probably have a tone on there, and we'll make it kind of an oddball tone so it's not likely that they're using that. So we don't hear Mexican taxis very often. Downlink 145.964. If you watch this.
Tell me you're joking.
Huh?
Tell me you're joking.
Why? I'm not. I don't know that they're from Mexico.
Face is hard.
I don't know that they're from Mexico. It could be Venezuela. My Spanish, no good. If you watch this, this will change with time as it adjusts for the Doppler. There is a beacon. It's on this satellite. It's the same as the downlink frequency because it uses that data under voice. You can sort of hear it. And there it tells you that. There are ways on this page, if you click on these, it will select all the linear sats. It will select them plus the FM. It will select it. This is without a doubt, the easiest way to get started if you're interested in tracking satellites. The other easy way is with an app on your phone, and there are half a dozen apps out there. I don't pay for one, I forget which one it is. I'll be happy to show it to you later. It tells you where, it basically tells you all the same information, it tells you where to point your antenna. I think that was that. Mark, if you will open another tab and go to amsat.org, just the regular version. The regular version, the North American version. You have to type in the little box at the top.
Space
Oh, okay. All right.
And here it says the AMSAT organization.
There you go. All right. I will update that page with information about it today. I have my slides too, and some other stuff, a bunch of things. If you click on satellite info and go to satellite status.
Current status?
Current status, yes, sorry.
Holy Moses.
That's everything that's up and what it's doing. This will move to the right as time goes by. If you scroll down further, there's spaces where you can enter your information. If you hear the satellite, if you hear two-way conversations, you mark it one way. If you hear the telemetry, you mark it another way. If it's the space station and it's the astronauts, you mark it another way. You put your call sign in, and then yeah, we don't know that, but don't click submit, please. Scroll back up again. Now, if you hover over those, any of those colored markers there, it'll tell you, well, it should, unless pop-up blocker's on. Yeah, it's supposed to tell you who's actually reported it. But you can tell what's active and what's working. So the blue stuff is what you want, because that means that there are two-way QSOs taking place on it. Red means it hasn't been heard from.
Your battery broke, so speak up.
My battery broke?
Your battery broke.
Earth is hard.
So this is the best place to find out what satellites are up and what satellites are working. Mark, if you will go back to the main page. Go under satellite info again. And go to communications satellites. And scroll down a bit. This has all the information for the various satellites that are up there. If you click, oh no, click on where it says frequency, click here for frequency chart. Yeah. And scroll down here. This tells you all the frequencies for the various satellites that are up there. It'll tell you the uplink frequency, whether or not it needs a tone. It'll tell you the downlink frequency. You scroll down a bit more, there's a couple more. So 50, PixSat is a new French satellite. It's not quite ready for prime time yet. And on and on and on. So all the frequencies you need to know are on the AMSAT website, including all the Chinese. All right, send me back to my presentation so I remember where I am. Yeah, that's our stuff for today. So we've got that AO91 pass. I don't think we're going to make that because I don't have my antenna assembled. If you're still here at 1144, we'll try at 1144. That's actually a little bit higher pass, and it's to the west. That'll actually be an easier one. There's the sample of the page. There's actually a good thing, and I'll provide a link to this document. This is a full document on working those Fox satellites, and it has everything you want to know about it, including how to set up your memories in your radio, because basically what you want to do is have the sender frequency in one channel, and then have on either side of that channel have some that are a little bit higher and a little bit lower, so that you can adjust for Doppler by changing your channel number. What kind of antenna do I need? I have an arrow antenna. It's in pieces there, which is why we're not going to make that satellite at 11. Do you have to spend $125 for a handheld satellite antenna? No. If you go to this guy's webpage, he's got complete plans for building this antenna, and you can do it for like 20, 30 bucks. And build it yourself. It's a wooden boom. These are brazing rod. He's got all the measurements for the spaces between the different elements and how to do the matching stuff, and it's actually pretty simple to do. It's not like when we had Oscar 13. When we had Oscar 13 and it was 35,000 kilometers away, you needed fair-sized Yagis and 100 watts at least to talk to those satellites. Not the case with the LEOs. The LEOs are only at 500 kilometers. That's only 300 miles. It's right there. There's no big buildings. It's line of sight to the satellite. But you usually need a Yagi. Have there been people that have talked to the satellites using handheld antennas with the handheld radios with the whip antennas? Yes, many of them. It's not an anomaly. It happens a lot. The reason it doesn't happen more often is because there's so many people trying to use the satellites. Oh, I thought I had one more slide. I think I lost this battery too, Mark.
Yeah?
Yeah, I talked this battery down and I've talked this battery down. Is there one more slide?
Note to self, check batteries next time.
Just using the equipment is good. So,
You turn your hearing aids up a couple clicks.
Huh?
You turn
Somebody
your
figured it
hearing
out.
aids up a click.
so, what do you wanna know?
Okay, question here. On the Fox series,
Yes.
that's a small cube, right?
That's going around, that's a
Going around.
full-size model.
Do they have continuous, is that a continuous program to launch those then?
They built 5 of them,
Are they gonna build any more?
not exactly like that.
Okay,
They built 5 of them, 3 of them are in orbit.
right.
2 more are hopefully gonna go up this year,
Mhm.
and then we'll have exhausted that. The next program is golf.
Okay,
Those will probably not be 1U, those will probably be 3U and larger, depending on what's in them. They will be basically multiples of that cube.
okay.
So no more Foxes after these 2 launched, but there's a follow-on program called golf.
Mhm.
So yeah, there is a program to do that. And again, I'm not covering all the other satellite programs that are out there, and there are a lot of them out there.
Now, the Fox was probably able to piggyback, wasn't it, with other launches?
Oh yeah, they don't launch, oh yeah, I didn't really talk about that. We've launched stuff from all different places. The last one went up from India, because they have a polar launch facility. They can get you into a polar orbit. They launched the last one. The one prior to that went on a United Launch, what's it, ULA, United Launch? Alliance, thank you. From Kennedy or Vandenberg. We've launched them on everything. When they launch these things, some of these launches have 100 satellites on them,
Okay.
because it's big. And they pop them all out. There's a variety of different launch adapters. There's one called a P-pod, where you load them in, there's a big spring at the end, and you just keep stuffing them in, and then when it gets a signal, it plop, 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 and shoots them all off into space. Yeah, so they don't launch those little ones one at a time, they launch them 5, 10, 15, 20, 50, 100 at a time. And that's the current way, it's getting crowded.
So, like the golf series, what is it going to cost to build a satellite, and what do they think it'll cost to launch one, do you know? No,
I
I-
just send my dues in.
Just in your deeds, okay.
And hope they have enough money.
But they're hoping the universities will pay a big part of it, don't they?
Or at least open doors, like this CubeSat launch initiative. If we were not partnering with universities, we would probably not get into programs like that. So, yes,
I have a very simple question.
yes.
With all of these launches, all of them in space, all the debris it took to get them there, what's the percentage of them colliding together in failure?
Remarkably small. Remarkably small. Part of that is because that guy, Kepler, figured out how to quantify those orbits. NORAD keeps track of, North American Air Defense Command, keeps track of those
So they-
very closely.
They designated a spot where you got in space?
Yes.
Figured that out.
And they make sure you can't just go and launch something, you've gotta have a plan. You've gotta know what the orbital parameters are, and there's gotta be space for you to fit in there.
And the frequencies also have to be coordinated.
Frequencies are coordinated by the IARU.
Uh-huh.
That has actually changed in the last few years. There were a lot of non-amateur satellites using 70 centimeters as their downlink for their telemetry that weren't amateur satellites. Supposedly that's not going to happen anymore, and it'll only be amateur satellites in the amateur bands. But the IARU through the UK version of AMSAT are the ones that coordinate all the frequency stuff. Orbital debris is a problem. NASA has an office now, there's an international agreement amongst all the spacefaring nations to make sure that you have a plan for disposing of your satellite. When its mission is complete, you need to, well, yes, or for some of the bigger stuff that's in geosynchronous orbit, they'll actually move it to a parking orbit once its mission is complete, and they sit in a known spot. And they're out of
The
the way.
satellite graveyard.
Satellite graveyard, yeah. Yeah. So yeah, it's a problem.
Target practice for lasers.
I'm gonna ask a question that might get me kicked out of the club, but.
All right, very good. We've been waiting for this.
Yeah, for a long time.
Yeah, thank you for
All
that.
in fairness, say aye.
My dues are not due. with, aren't these, I mean, outside of a few experiments and stuff like this, aren't these just fancy space-bound repeaters, toys that satisfy somebody's ego?
I don't know about the ego part,
Yeah.
but otherwise, yes. Yes, particularly the FM ones, they're repeaters. They're pretty crowded right now, and sometimes the operators are not as polite as they might otherwise be.
I've noticed that.
You really want to do, we didn't talk about it, but you really want to, when you operate, you want to do full duplex, because you can hear your transmission coming back. And there are a couple radios around, the Kenwood TH72 is full duplex. You can listen to your own signal coming back down while you're transmitting. And that's the best way to do it, because then you know you're getting in. Can you make it without full duplex? Yeah, you can. But full duplex is better. But yes, and if you've done contesting on HF, you know what those rapid fire QSOs are like. A lot of the FM satellites are just like that. It's hello, goodbye, they exchange grid squares, move on to the next. Because you've only got 10 minutes that it's in your window, and there's, for that whole 10 minutes, there's guys that are falling out and there's new guys coming on. It gets a little chaotic. And yes, it's an FM repeater in
I'm
space.
still in the club.
Yes, you are.
Say it would do stuff.
The linear satellites that support more than one QSO at a time, because there's a pass band where you go up on lower sideband, come back down on upper sideband, or UCW. They are a lot less FM repeater-like, although they are still a repeater in space. But yeah, that's not an unreasonable question. I don't know what the ego part plays.
Well, there's so many of them. I mean, it's like, how many is enough?
They don't last forever. Oscar 7 notwithstanding, they don't last forever. The estimated lifetime for the Foxes is like 5 to 7 years. And then they don't have rockets on them. So their orbit will decay to the point where they will re-enter the atmosphere.
So you're saying 5 years?
5 to 7 years.
And the estimated cost of putting that up there is?
You know, that's something I should have looked up, and I don't know what the number is. I don't know what the number is. For those little ones, it is not $1 million.
Okay.
I think, it seems to me they were running a fundraising thing, and it was in the neighborhood of $150,000 for the launch, not including the cost of building the satellite, which I expect is a lot smaller cost.
Yeah.
MSAT says the CubeSats are 100,000 full price, but negotiated based on educational value.
Right, yeah.
Sand.
Right, yeah. So yeah, so they're not cheap, but for those of us that like them, they're fun.
Why don't we have a ScarSat?
Well,
Now you're out of the club.
but if we can get him to write it into his will to bequeath the money, we will. In fact, we'll call it Jeff's Sat.
Jeff sat here, that's the only sat we're gonna have.
Okay. What else do you want to know?
Still an observation, there's so many, but yet there was none in, we're in the footprint while we were talking. So there aren't so many, there's only limited coverage, very little.
That footprint covers about most of the continental U.S. ones in the right
When you
orientation.
brought it up, there was 15 minutes until there was gonna be one. And
Yeah,
they
but-
were only gonna be in the.
You notice that I cut down the number of satellites on that screen just to unclutter the screen. There's actually a lot of satellites up there. There is a series of Chinese satellites, XW something, and that actually stands for something in Chinese, that were launched in one of these Peapod type things, and they're all in a line. And you can work them one after another, and you can talk to somebody for like an hour,
Then
because
they
another
may
one
not be
keeps
in-
coming over.
And they may or may not be in frequency when it's speed.
No, they're handsets. No, they're amateur. They're on the regular amateur band. But they're in an orbit. They're in sequential orbit. So.
That was the port that between them.
Oh. So yeah. So
They have satellites.
you had your hand up. For,
Yeah, so like the walkies that do just a 5 kz step, so you just round up or down to the next.
exactly right. The Baofeng. Some of the Baofengs will actually do 2.5 kilohertz steps, and that gets you closer. You can put more steps in there. There is an AFC on my frequency control on the receiver that does a pretty good job of dragging you lower. So, it works pretty well.
So real quick, I'm just curious, if they don't have thrusters on them, how do they stay up there?
They don't, eventually they'll deorbit. The atmospheric drag will
If
bring
they
them
stay
down.
up there for 5 years, how are they staying up there?
Magic. No, that's right, it's just like you said. Okay.
That initial.
Inertial energy, but